Hi everyone, today we are doing logarithmic functions. Now this is y equals log of x with the base of 2. Just like the exponential graph, but a bit different. Now firstly, there is an asymptote, just like the exponential, but instead of the x-axis, it's at the y-axis. Secondly, everything is positive because x cannot be less than 0. So quadrants 2 and 3 are going to be left empty. Now, as x increases, y increases at a decreasing rate. That means the graph is sloping, but it keeps going up and it keeps going to the right. On the bottom, opposite story, although the asymptote is at 0, it keeps increasing and increasing, or decreasing at an increasing rate. And x-intercept is always 1, just like the y-intercept is always 1 when you're doing an exponential graph. So this is the exponential graph, and you can see they're closely related. It's what we call the inverse. So that means they are reversible. So let me give you an example. So first of all, f to the negative 1, that means inverse. So let's say if we're doing y to the power of x, we substitute 5 and we get 32. Now if we were to do the inverse of that, so that's the inverse of exponential is logarithms. So we're going to do log 32 with the base of 2, and then we get 5. So we got from 5 to 32, and then we came back. We reversed it. Also, domain, range, everything is infinity except for the domain, which it doesn't go into 2 or 3 quadrants. Next one, graphing log functions. So we're going to graph fx equals 2 log x with a base of 4. Now, first of all, we know what the graph looks like. It's going to look like any other log graph. Let's find the x-intercept. Now I know that x-intercept is going to be 1 because that's always what the x-intercept is. But if you ever want to use an equation, 2 log for x equals 0, since the y value has to equal 0. Now that's the same as 2 times, which means if this side equals 0, then this side 2 doesn't really matter. And log equals 0 when x equals 1. Alright, we're going to find one more point. Find an easy point. So I'm going to do log 4 with the base of 4, which is going to equal 1 and times 2, so 2. So 2 and 4, or rather 4 and 2, is the other point. Next one. We have got a constant term here, so whatever log x with the base of 4 is, we're going to move everything down 2 spaces. Graph looks the same. So instead of the x-intercept being 1, we're going to put it here. So 1, which was the x-intercept, but we've gone 2 spaces down, so negative 2. And I should really say c is equal to negative 2 there. Now we have to find one more point. Let's find the x-intercept. So x-intercept, y has to equal 0. Four to the power of 2 is 16. That means x-intercept is 16, and this curve is way out of scale. The other way you can do it, if you ever get confused, is use a table. So there we go. That's -2 or 1 and -2. And that's it. And for this one, you can use this equation like we did last time. Now let's do question 3. So we're going to draw two graphs. The first one, we know what it looks like. Now the second one, it's -x. What that means is that whatever's in the bracket has to be positive, so x has to be less than 0. If it's negative, the two negatives cancel each other out. So since x can only be negative, it's going to look like that. And if you want to make a table, and they are symmetrical over the y-axis. Last part, we are comparing logarithms, and whenever we're doing logarithms, and they don't tell you the base is 10. So every increase of 1 means an increase of 10 to the power of 1. So if you increase by 2, that means 10 to the power of 2, 100. So let's do Newcastle, which is 5.6, and Swan Hill, which is 4.8. There is a difference of 0.8. That means a difference of 10 to the power of 0.8, which is 6.2.